All right. Yesterday we talked about how to graph exponential functions using a table. It looks something kind of like this for 15. There's a better picture. There you can see the graph. So if you don't remember how to do that, go ahead, watch that video to refresh you on that. Today we're going to talk about how to graph exponential functions without necessarily filling out the table. We're going to talk about some rules that we can rely on to make this work for us. The first thing we have to talk about is a generic form for exponential functions. The generic form for exponential functions will look like this. F of x is equal to a times b to the x plus c. You'll notice in the ones we did yesterday, most of the time, a and c were 1 and 0 respectively. They weren't there. Today we're going to talk about what happens when they are there. First thing we have to say is that b, I'm going to do a lowercase b because that's just better teaching, it's consistent. B has to be bigger than 0. If b is not bigger than 0, we have a problem. For example, if we had something like -5 to the x, if you graph that in Desmos or something similar, it'll end up kind of looking like this. It'll be a bunch of points. It'll make kind of like it kind of looks like a connect to the dot trumpet. That is the kind of function that you would talk about in college. So we don't need to worry about that right now. So for our purposes, assume that an exponential has a b bigger than 0. If b is in between 0 and 1, it will follow a decay pattern. You'll remember that a decay pattern will look something like this. It starts up and then ends down, decreasing. There will also be some asymptote, some line that it'll get infinitely close to but never quite touch. Okay, if b is bigger than 1, oops, I did a capital B again, didn't I? It will follow a growth pattern. I'm going to write it will growth just because I want to stay consistent with the words we've used before, even though I do acknowledge that isn't proper English. And you'll remember that a growth pattern will look something like this. We put in our axes. We'll have the function start small, and it'll get bigger over time. Once again, there's going to be an asymptote that it will not cross. Okay? To figure out the y-intercept of an exponential function, it will always be this formula. It will always be a plus c, every time. The reason being, if we plugged in 0 for b, like we do for the y-intercept, we would get a times b to the 0 power plus c, which would be a times 1 plus c, or a plus c. We can go ahead and write that as a coordinate point. So when x equals 0, y will equal a plus c. That will be like our starting point for when we graph these. Another thing, the asymptote will always be a horizontal line and it will always be at y is equal to negative, no, not negative, just positive c, whatever c is. So we can simply look at an equation and figure out a whole bunch of things about it really easily. So for example, if we had 5 times 2 to the x minus 2, we know right off the bat that our base, our b, 2 is bigger than 1, so this is going to be growth. And we can figure out that the y-intercept is going to be 0, 5 minus 2, which would be 0, 3, and that the asymptote would be at y is equal to -2. So we could graph that fairly easily from this point. Let's put in our axes. We'll say that this point right here is -2. And we can just, I'm going to put my asymptote in red. It's not really there, but it's helpful to remember it being there. We can go ahead and put in our point 0, 3, our y-intercept, and we know that it's going to follow a growth pattern. So as we go towards -infinity, it's going to go on there. And as we go up towards positive infinity, it's going to grow infinitely, which means it'll look something like that. Now, I would call that a really good sketch of the graph, but it isn't the most accurate graph. So let's talk about how we could increase the accuracy of this graph to be more reflective of what the exponential function would actually look like. Now, when we do exponential functions, it's helpful to think about what f of 1 would be and what f of -1 would be. So basically, that would be this point here and this point here. Now let's figure out what they would be a little bit more accurately. The generic form for this will be f of 1 is always going to be a times b. F of -1 is always going to be a divided by b. All right? To be clear, that isn't necessarily going to stay, that's relative to what our starting point is. If you wanted to be complete about it, you would have to add the c to both of them, just to make sure that it's all the way complete. But I kind of like to think about just the first part, and I'll explain why. So for example, if we have this graph that we just did, 5 times 2 to the x minus 2, and I wanted to do it more accurately, I'm going to slide down to give us a little bit more space. We can put in our axes. We start at 0, 3, and the next point would be f of 1. So if we wanted to go to f of 1, we would see that we have a times b plus c. So that would be 5 times 2 plus c. So when x is equal to 1, this is equal to 5 times 2 minus 2, which would be this point right up here. So it would be 5 times 2 is 12, minus 2 is 8. So 1, 8. 3, 4, 5, 6, 7, 8. So, relative to this, we increase by 10. Okay. We can do the same thing going down. We have 5 over 2. Should be going down 5 halves. Our next point would be right there. You would flip those for decay, meaning if we were pretending this is a decay function, we'd go down 10 and up 5 halves. But this is a growth function. From there, you could connect the dots together, and you'd have your graph. All right, as always, let me know if you've got